In the never-ending search for more performance, there is one thing you rarely see championed: data-oriented design. Everybody wants to use object-oriented patterns. And let's be fair, there is nothing wrong with that. It's accessible, easy to understand, and lets you ignore some of the more technical details of game development. There are plenty of cases where object-oriented programming is not only good enough, it's ideal. Let's say you're making a level-based game. There are about 10,000 objects in the level. It's a pretty big level, but it's self-contained. These objects all have different functionalities, do different things, and as a general rule, do not operate on tick or need to update every cycle. In that scenario, object-oriented programming is perfectly fine. You gain very little by adopting data-oriented design patterns. Now take that same level, but make all 10,000 objects tick, and they run the same or similar enough code that their behavior can be expressed as a more generic calculation. They still represent different things, but the logic is shared. This is where object-oriented programming can start showing its limits. The issue isn't that object-oriented programming is bad. It's that the memory layout and indirection it often encourages can become expensive when you scale up large numbers of frequently updated entities. This example, while slightly exaggerated, stops being unrealistic the moment you move to open-world games, where you might have tens of thousands of entities in the world. The logical reaction is, just don't update them. And you'd be right. This will do wonders for performance. But what if you want the world to exist and function whether you're looking at it or not? What if you want persistence? What if you want the world to feel alive? Are these achievable using object-oriented programming patterns? Yes. Is it possible to fail at this using data-oriented design patterns? Also yes. But what data-oriented design undeniably gives you is better control over performance characteristics, easier time slicing, more predictable cache usage, and designs that are generally more friendly to parallel processing. It doesn't magically make your game fast, but it gives you tools that scale better under heavy load. Data-oriented design is, simply put, designing around data and access patterns rather than around objects. In object-oriented programming, an object typically owns its data and the functions that operate on it. In data-oriented design, you instead ask, how is this data actually used? You then store related data in contiguous memory structures and write functions that operate over large batches of that data. Instead of one object, one function call, you often end up with one function, many pieces of data. Because memory is laid out contiguously, the CPU can cache and prefetch more effectively, and you avoid excessive pointer chasing and virtual dispatch overhead. A common comparison is an array of structures versus a structure of arrays. It's not that one is universally better than the other. What matters is memory layout, access patterns, minimizing indirection, and reducing unnecessary branching or virtual calls. Let me show you how this works in practice. I have 3 versions of the same function. 2 are written in an object-oriented style. One with minor caching and reduced data reads where possible, and one more straightforward version. The third uses data-oriented design patterns. Each processes 7,560 entities and updates when relevant.
These are two different implementations of doing the same thing. Like it's the same. This one is slightly faster, not a lot. But I'll show both. see here it says how many entities are being calculated this loop, and yeah, it's basically just a function that just moved. But see, since it's not cached, you can see. We'll see it just now. See how the edges. There you go. That's not the point. That's not the point. What we are paying attention to is the green line or the green number. This one or this one. They're basically the same. And like if you can see, like this is just all the values being set. It's about 10 milliseconds and just turning away by itself. Like you cut it in half. Like, but that's not really the point. So you can see 6 milliseconds for this basically. Let's just let it stabilize. This is like the absolute best case scenario for this. The absolute best case is about 6.5. Okay. This is the second one. So the only real difference here is it doesn't use this. It doesn't. Instead, it just just stores it. Uses this value here. That's pretty much it. Okay. Remember, it was 6.5 milliseconds at like best case scenario. This is the advantage of this method as well, though, is you can see there's no like sudden, like it's all uniform because the value is always correct. Simply because you're caching it. You don't have to apply it, but you're just caching it. And let's wait, see what the best case scenario here is. See, it's below 6 milliseconds, which is good. It's good. Obviously, once again, applying the changes to the world is the thing that is nuking performance. It's actually insane how much of a difference it makes just applying the data. Obviously, this is a very unrealistic case of having 7,560 things like that. That's a lot. However, why not go even further? See, here's let's see how long till we break it. So we do. Let's do 2. Like this is probably gonna drop to 30 FPS, I think. This is how many is this? This is like 30,000. Where did I change the right one? Yeah, I changed the right one. This is like 30,000. I'm still using the better version. Is it 30,000? Wait, let me check. How many is it? That's 30,000. That's how many it is. It's a lot. Obviously, the green line. Pay attention to the green line. The green line is the important line because that is the price, the price that is being paid you can see best case scenario for 30,000 is, where is it still dropping? Best case scenario 30,000 using the standard traditional object-oriented methods where the object, well, in this case it's a bit of a gray area, but it's still functionally the same. 21, 22, 21, 22, and if we're going to turn around, it's going to jump all the way to 40 at least. Oh, no, see, 40, almost. Like, just setting the data is like half the cost. That's like such a like, to me that was such an eye opener. Like, obviously it's I mean, it's kind of obvious in hindsight, but like, yeah, just look at that, like, dropping it, like halving it, like, it's insane. Just setting the data, like, it's, well, this is just the update frame. The render, I don't know. Okay, so now that we've done that, let's look at the data oriented design one. This also like uses just uses data to count and counts the entries and outputs the total amount. Like it's the same. Like I need to show, like, this was, remember, this was best case for this was 5.5, and the previous one, this is still 7,560. Like, it's you see there are no components on these. In a real world situation, you still would have components on these because, or something to store data. This isn't just, you wouldn't just normally do it this way. This is obviously very unrealistic, but you know, it is what it is. But anyway, so as you can see, it's basically just a struct, a point, so that I use to apply it. This, technically speaking, you should just do it this way. That way you don't have any pointers. However, this is slightly slower, like by half a millisecond. I can show how much slower it is. Let's just show how much slower it is. But like half a millisecond, like it's not that much. As you can see already, we're on 4. I don't remember what we were the previous one, but it was more than that. This is by the way the slower way of doing this. It's also the quote unquote safer way to do it, because you're not actually working with pointers directly. So yes, we can. Let me just move this aside so you can see 7,000. That's like, it's huge. Just look at that. Look at it. That's it's like 1.5 milliseconds, like that. This is the green line. The green line is the one we care about. Obviously, there's no components because there are no components. But that's insane. Like, and obviously, if you look at it like this, you get like 6.5. Obviously, this is the slower version. If we do the faster one, so like how much? Like 6.5 maximum for this case. And if we do the faster one, it's not that much faster, but it is faster, like measurably faster. You won't notice it though. Like when it's not applying, you won't notice a difference. Okay, Okay, so as you can see, like it should still drop to like 1.5, 1 point something. It should be about the same, like margin of error kind of range. It's about the same, like 1.3, 1.4. So it's the same. So if we turn around, remember it was 6.5. It's gonna be, if I remember correctly, like below 6. Let's see. Yeah. No, it's below 6. See. So it's about half a millisecond faster. You won't actually notice that, at least not on this scale. And realistically, you actually won't do much more than this, usually. Applying, which is like applying data to 7,005. Like, once again, look. But this is like just the calculating the data. Like, this is full calculation. Like, it's 2.2 milliseconds. Just turning around, and it goes up to almost to 6. Almost to 6. Like, it's 3 times the calculation cost. 3 times. Just the setting of it. That's ridiculous. However, let's break it even. Let's see how many we can do. I think we did 30,000 with the other one. See how many we can do here. I think we'll just go straight to 30 as well. Was 4, wasn't it? Was it 4 sets? No, 4. See, I can't just duplicate the root node for this one, because otherwise you won't be able to see it, because since the way I set it up, it works in like local space, which kind of sucks, but that's fine. Like, it doesn't change much except for like this part. So this is about there should be about 30,000. Yeah, it's like 30,000. I don't remember what the exact frame rate was for the I don't remember what the exact frame rate was. Let's go. So this one also thought 30,000. See how much we get for 30,000. Remember 30,024 and 60. Not 60, but yeah, close enough. Like, so this of 30,000 with 60 with 10 milliseconds. Like, it's remember it was 21 milliseconds best case scenario. 21. We are not writing the data. We are at 6.5 for 30,000. Like, that's almost 4 times faster. Dropping to 4. Now this is obviously like nothing changing, which is quote unquote best case scenario. We are actually not even being bottlenecked by this. We're getting what's slowing us down. Actually, I have no idea how this works. I just know this is the update. And if we go to setting it, we in like the setting 30,000 objects, we match the best case scenario of the quote unquote object oriented method. This is like, it's insane. Like, it blows my mind. Like, and the thing is, like, usually you won't even set this many. Like, you'll set like maybe 200-300 per cycle, maybe, and yeah, it's just that blows my mind. However, we can go even further beyond. Let's do 60,000. I just hope I don't crash this. 60,000. 60,000. 60,000. We're gonna do this. This is what I call very unrealistic. Please don't crash. Come on, baby. Come on, baby. You can do it. You can do it. Come on. Oh, there we go. Come on, there we go. This is now like 60,480, I think. If it, like, one day when it catches up, that'd be nice. This is obviously, if you're doing this, setting this many variables, you're doing something wrong. You might need to reevaluate a few life choices. That's a lot. I'm just making sure it's safe. Okay, minimize. Okay. Okay. That's a lot. Like, that's insane. Like, that's a lot. And it's still, like, the idea isn't really to, like, the idea isn't to say, like, oh, this or that. Like, it's just this, like, if you're gonna update a bunch of characters, like characters, for example, let's say you have, like, yeah, I don't know how to put this. Like, this is just absurd. Like, I'm pretty sure the object origin wouldn't even run, or maybe it will run, but just really badly. Like, this is terrible. This is actually just terrible. Like we're like 15 frames a second or something. Like, it's bad. But, like, once again, this is 60,000. Why on earth are you setting 60,000 objects? That's just stupid. Like, and this is perfectly playable. It's not, like, ideal, but it's fine. There are 60,000 objects. It's just, and if we let it go, like, to like 12. Now it's just, nothing is changing, so now it's just going really fast. Like, that's just, like, how do you justify not using this? Like, even if it's just like 2,000 things in the world or something, like, it doesn't have to be 60,000. This is literally free performance. That, like, we're literally at 60 FPS, and we're calculating this many things in the background. It's absurd. It's absurd.
I'm not advocating that people abandon object-oriented programming. Most of the time, unless you're running a large-scale, constantly updating world, you do not need data-oriented design principles to deliver a good experience. Instead, focus on caching your data, reducing unnecessary indirection, avoiding redundant reads and writes, staggering or batching updates when possible. Reading data itself usually isn't the main issue. Modern CPUs are usually very good at reading, especially cached data. The real performance cost often comes from memory access patterns and unnecessary writes, cache misses, and forcing the CPU to constantly fetch new memory lines. If I had to pick one takeaway, Don't write out data unnecessarily. It is rarely worth it. Limit non-critical updates. Stagger work where possible. And remember, it's not the math that kills performance. It's how and where the data is stored and updated.
I figured I should do this in blueprints as well to show how that it doesn't just the benefits aren't just limited to C++. Now this is the object oriented. All it does is this, and then it basically just uses. It's the same logic as the C++ code. It's identical, and we're doing this in like best case scenario as possible. We're running in game mode, and like I think you can still get some if you actually build it, but I'm not going to do that. So this is I'll show now how many this is, but it's the same logic, and once again if you look away it decreases the cost. And this is the one that's running like the standard workflow you would do for Unreal. As you can see here, we are being bottlenecked by the game thread. This is the actor logic essentially blocking performance. I don't have the best GPU, but it is being blocked by the game thread. And once again, it's the same problem. You turn around and you're setting the data. If you're actually setting the location, you're basically paying about 7 milliseconds. No, it's not a lot. This is also admittedly not 7,000. I think this is about 2,000. It's not that many. But it's more or less the same. Now for this version, this is the let me go through this first. This is where we spawn. I'm just going to switch them around. So now it's going to go for that one, and we start setting the array elements. Connect this. Once again, same function. It's the same thing, like it just loops over each element, and it only sets it if I'm looking at it. Like the idea isn't to benchmark setting objects. The idea is to calculate background. Like I don't know if I said that enough, but it's for background things. And this just sets it, but this is just to make sure that it doesn't sit when I'm looking at it, so I can get just the raw data calculation. And obviously this is just this. Like there's nothing special about it. And yeah, like it spawns 2,000. Displays this is to make sure I actually spawn the right one, because I keep forgetting. It says some 2 meters apart. I don't even know, it's for 20 rows and 20 columns. And then just setting the array element with that, so that it's actually stored in the array at the correct index. And when you just run this on tick, that's it. That's the only difference between this one, which just, sets the values and then calls this function. It's the exact same logic, except it operates on an array of objects rather than the object running itself. So we got, I believe, 17 milliseconds, and we were blocked by the game thread. Okay. So you can see now we're basically we're basically running at, while we're setting it at the same speed the other one was running as its best. Like it's still throttling the GPU, but it's not as bad. I don't know, it's throttling. It's still we're still CPU limited. Not. I can see it's dropping down now, so it's like we're hitting 12, so it's even while setting values. But I think it doesn't matter. So if we go here, right, we're looking at this. Now the game thread is 9 milliseconds. We are no longer blocking this is no longer CPU limited. So basically, it doesn't scale as massively as it does in if you code it in C++, but there's still performance to be found. Like and as you can see, it's actually quite simple to set up. Where was this? Okay. Like it's very simple to set up. Like, once again, it's just this. It's just this, and then instead of doing all this in one object, you do in many objects. You do all this in one object. In this case, in the level blueprint, but I don't think that matters that much. You could create a singleton for this. I think. I'm not sure if you can do that in blueprints, but yeah.